Yeah, hi there, Year 13. I just want to quickly go through the Education Perfect test that I set you. A good number of you didn't do as well as I was hoping, so I want to quickly go through the answers to make sure that we're all on the same page. And so it says, to make a capacitor, Cassie places a thin layer of rubber, so I imagine that's the black material there, between two 1.20 meter squared, so that's an area aluminium plates, and they squeeze the sheet together so that it has a thickness D and a dielectric constant epsilon R. And so we go, what equation? And we're looking for capacitance C, and we come over to our formula sheet and we're saying what equation has a C, an epsilon R, and epsilon naught, an area and a distance. So that's the formula I'm going to use there. I'm then going to substitute the numbers. What is epsilon naught? It's permittivity of free space. It's a number given to you on your formula sheet. And so if we open up our formula sheet, permittivity of free space number 8.85 times 10 to the minus 12, and so that's where that number comes from. And then the area is 1.2, the distance between them is 1, and then we times it by the dielectric constant, so it's 8.9 times better than just air, and that should give you an answer of 9.45 times 10 to the minus 7 farads. The next question, Cassie sets up a battery which has a switch and a 3 ohm light bulb in series. The battery voltage is 6.02 volts. When the switch is closed, however, this voltage, the terminal voltage, then drops to be 5.85 volts. Why? Well, when we look at that battery, it is a battery like so, but then it also has an internal resistance in it. So if we were to ask what's happening inside this blue box, well, there's a power supply which has an EMF which is 6.02 volts, and then when a 3 ohm resistor is added to it, then there is voltage lost across this resistor, which is equivalent to IR, where R is the resistance of the resistor. So essentially it's a cheat level question, something linked to voltage being lost by the internal resistance inside the power supply. Cassie measures the current through the circuit to be 1.89 amps. State the EMF, so we've already stated the EMF above, so the EMF is 6.02 volts. So that's part 1. Part 2, and show the internal resistance is approximately 0.09. So I might do it up here. And so if we attach this, I appreciate it as a light bulb, not a resistor, but for the purpose of what we're doing, it doesn't make too much of a difference. And we've got 5.85 volts here. And so I say, well, what is the current? So I is voltage divided by resistance. The voltage across this is 5.85. The resistance is 3. And so if we go 5.85 divided by 3, I get 1.95 amps. So we're getting 1.95 amps going through the circuit. And so I know what that I is, and I know what this VR is, because VR is going to be epsilon minus the terminal. So if there's 6 volts here, there's 5.85 volts here, then I know that 6.02 take away 5.85 will give me that voltage here, so which is 0.17 volts. And I'm looking for the resistance, and so R equals V over I, 0.17 divided by 1.95 gives me 0.087 ohms. And what were they looking for in their answer? 0.89. Yeah, that's fine. So that is a merit question. Cassie now adds a capacitor. So we see a capacitor over here. capacitor over there in series with the battery and closes the switch. Cassie measures the voltage across the capacitor as it charges. Use information in the graph to determine the capacitance. So you want to say, well, it goes to 6 volts, which is V max, and I want to say, well, what's 63% of 6, which is 3.78 volts, and so I come up to 3.8 volts. I come down. How about I try that again? That's 2.8 volts. 3.8 volts. Okay, so we're getting a time constant, tau, equals 1.0 times 10, and a lot of you missed it, minus 5 seconds. A lot of you used, I don't know, 5 seconds as your time constant, which would be okay, because after 5 time constants, it approximately reaches the maximum voltage. So if you went 5 divided by 5, you would have got the same time constant as 1. Now, once we know the time constant, then we're going to use tau equals RC. We know from up here that there is a 3 ohm resistance, and it's already told us that there's an R of 0.09 ohms in there, and so that's R total is going to be 3.09 ohms, and so then we're going to use tau equals RC. We know this is 1 times 10 to the minus 5 equals 3.09 C, and so you should get this number here, and that was worth, again, a merit. Next question, Cassie discharges the capacitor, removes the light bulb, and begins to charge the capacitor again. So essentially we have a power supply. Wow, Mr. Harris learned how to draw circuits. So 6.02 volts, 0.09 ohms, and so the resistance has gone, R has gone from 3.09 ohms to 0.09 ohms. And if we've got tau equals RC, has the resistance changed? Yes, it's gone down. Has the capacitance changed? No, because the capacitance is dependent on the physical components of the capacitor, so it's dependent on the area, which hasn't changed. It's dependent on the dielectric, which hasn't changed, and the distance between the plates, which hasn't changed. So the capacitance is the same, and so this is fixed. And so what's the time constant have to have gone down? So yeah, so use physical reasons to discuss the aspects. So whether the capacitor will change, nope. Whether less energy will be converted into yes, because there is a lower resistance, and so P equals I squared R. If the resistance is smaller, then the amount of power being wasted is also smaller, and whether more energy will be stored. Will more energy be stored? That's an interesting question. So the capacitor will charge more quickly because the time constant has gone down, so the current, because the resistance has gone down, so the current is higher, delivering charge to the plates more quickly. No energy would have been converted to light, but more energy would have been converted to heat passing through the internal resistance of the battery. Yeah, that's a good subtlety, because I would be dramatically higher because we've got V equals IR, and R has got really small, and the supply voltage epsilon is the same, so our current's gone really high, and so we're going to have a lot more P equals I squared R, a lot more current, and so a lot more power wasted in here, but no more wasted in our light bulb that doesn't exist. So the same amount of energy will be converted in the charging process. It just happens faster. The fully charged capacitor will store the same amount of energy, because Q is this, because C is the same and V is the same. That's actually quite tricky. Excellent. Cool. Next question. The circuit diagram shows two batteries connected in a circuit. The internal resistance R1 of the 11 ohm is 2.7, and the internal resistance of the other one is 2.5. So which one I switch to a closed? and switch tree is left open. Show that the current in the circuit is 0.031. Cool, so basically these two are closed and we want to know what the current is. And so we walk around our circuit, and so it depends on which way you want to walk around the circuit. If we choose to go that way, and I'll start here, and I have to decide which way the current's going. This is a higher voltage and the internal resistance is much bigger, so we'll assume this one wins and the current is going to go that way. It could be wrong, and if it's wrong then it's negative, that's fine. And so I'm going with the current, and so it's going to be minus 5i, going with the current minus 2.7i, going from little to big, plus 11 from big to little, minus 10, with the current minus 2.5i minus 20i equals 0. So I've got minus 5 minus 5 minus 2.7 is 5 minus 2 minus 2.7 minus 2.5 minus 20, and so I get minus 30.2i, and I get 11 minus 10, which is plus 1 equals 0. So I get 30.2i equals 1, or I equals 1 over 30.2, which is 0.03 amps. Boom, with a merit. The next question, 2b, the circuit diagram shows two batteries connected in a circuit. The resistance R1 is which direction is the current going to be flowing? And so I've got a positive answer to this question here. And because I've got a positive answer, the current must be flowing in that direction, which is anti-clockwise. And so anti-clockwise, because well, you could argue it from two positions. You could argue it from the position of this has got a higher voltage, and so it's going to win, and also argue it from this this Kirchhoff's voltage law equation. And next question, 2c. The circuit diagram shows two batteries connected in the circuit. The internal resistance R1 of the battery is there, and that hasn't changed. So by Kirchhoff's current law, the current going through S3 is 1.87. Okay, so because, sorry, that was just me having a bit of a think. Because all three switches are open, this now changes the dynamics, and so we can't use the above circuit. And so let's see if we can just use an A circuit. So if I start here and I predict the current's going to go this way, I'm going to call it I1. I could be wrong, that's fine. So we're going with the current, so it's going to be minus 20. I1, you can call it I7, you can call it whatever you want, minus 2.5 I1, go from little to big, plus 10 equals a crazy squiggle, equals 0. So minus 20 minus 2.5 gives you minus 22.5. So 10 equals 22.5i. So I1 is 0.44 amps. I've just noticed I've called that I2, so maybe I'll call all of those I2 just so that I'm the same as those answers over there. And so that's helpful. That tells us that current, but it doesn't tell us this next current. So I have to do my next current, and I'm going to call this one I1, and I'm going to call that loop B. Doesn't matter what order you do them in, it doesn't matter which direction you go, and I'm going to start here, and I'm going to go with the current, so I'm going to go minus 5I2 minus 2.7 I2. I'm going from little to big plus 11. Now I'm coming back around. I'm going from big to little, so minus 10. I'm going against the current, so plus 2.5, and it's I2 this time. I'm going against the current, plus 20 I2, and that equals 0. So let's see if we can simplify this down. So I've got minus 5 minus 2.7, so that gives me minus 7.7 I2, plus 11 minus 10 gives me plus 1, and then 2.5 I2 and plus 20 I2 gives me 22.5, and I know I2 is 0.444444, and so that's the same as they're saying plus 9.999 recurring equals 0. So that's going to be, it's basically 10 plus 1 is 11. So I've got 11 equals 7.7 I2. 11 divided by 7.7 gives me an I2 of 1.429 amps. We're nearly there. This must be, wow, it's only with near it. Crazy. So now I know I1 is I1 equals 1.429, and that was a positive number, so I was going that way. I've got I2 here, which is 0.44 amps, and so these two both go in, and so it must be this one here is our I3, and so I3 must be I1 plus I2, which add those two together, and I get the 1.87 amps. I would have typically thought that was with excellence. There's quite a lot of steps. Explain what effect a changing internal resistance has on the power delivered to the 20 ohm resistor. So we've got a 20 ohm resistor. The 10 ohm battery starts to go flat. This is caused by an increase in resistance. So this resistor here R is going higher. Explain what that will have on the effect to this resistor. This is resistor here. Okay, so we're essentially saying that the voltage here across these terminals, V terminal, is going to go down because you've got V equals IR, and that resistance is going up. So the EMF of the battery will stay the same. Yep, so the EMF 10 volts will stay the same, but the internal resistor will increase. The branch 2 will increase, so the current will decrease. As the current through the 20 ohm resistor decreases, the voltage through the resistor will decrease. The power delivered to the resistor will drop, and the voltage power delivered to the resistor will drop because of the drop in voltage and current. Okay, so what I'm gathering is that you can basically write off that because S1 is now open, so that whole top doesn't exist, and then you've got this S2, S3 are closed. Yeah, I suppose their answer is right. So they want to link to power output. Okay, cool. So hopefully that was helpful. That's video answers to the education purpose test. Thanks, team.